Thank you. Let me begin by thanking Peter Sarnath for inviting me to give this seminar. It's been a while since I was here. I was here in 2006-07 for a year. So it's more than 15 years. Good to be here. I guess I lectured in the same room then also.
Same lecture.
No, in fact, I have been thinking about this for a while. There are some new things, but not from those days. Okay. So considering the restriction of a representation of a group to one of its subgroups, such as SON+1 to SON for a local field has been a very fruitful direction of research, especially through its connections to questions on period integrals of automorphic representations. So period integrals are integrals of this kind, integral f of h dh, where f is an automorphic function on the larger group G. So the period integrals are typically related to some L values, and that is one of the main reasons why these questions about branching laws have a lot of interest. But in the lecture today, I will restrict myself only to local questions, and therefore there would be no L functions. The question for local fields amounts to understanding this Hom space, Hom pi1, pi2, for an irreducible admissible representation pi1 of the larger group when restricted to the smaller group. So which means that one is trying to understand this Hom space. The first important result proved is the multiplicity 1 property, which is one of the first key properties, that the dimension of the Hom space is less than or equal to 1. So surprisingly, this is rather, I mean, not such a classic result, but by now it has become classic. It is at the basis of much development. It's due to Eisenberg, Gurevich, Steve Ellis, and Schiffman from 2010 for non-Archimedean fields, and later also proved for Archimedean fields by Binyong Sun and Cheng-Bo Zhu. It may be mentioned that before the full multiplicity 1 theorem was proved, even finite dimensionality of the multiplicity space was not known, which were later answered in greater generality in this book that was written by Yannis Saklaridis and Akshay Venkatesh. So I think they have a lot of general theorems which include finite multiplicity. For infinite dimensional representation, which is what we are mostly dealing with, there is also the possibility that this multiplicity may be identically 0. So, you know, it may be identically infinite, and it may also be identically 0. Somehow infinite dimensionals one could not be so sure to begin with. But eventually one knows that they have some, they are less than or equal to 1, and they are typically 1 in some ways. So with the multiplicity 1 theorem proved, one then goes on to prove a more precise description of the set of irreducible admissible representations for which the Hom space is non-zero. So this is not the intent of this lecture, but there's rather complete knowledge about these when the Hom space is non-zero. These have become available in a series of papers due to Walsh-Purgey and Moeglin-Walsh-Purgey for orthogonal groups, and Bujar-Plassi for unitary groups. And there are many papers, so there are some sample papers which I list here. Okay, given the interest in the Hom space, it is natural to consider the related X spaces, Xi, pi1, pi2. And in fact, homological algebra methods suggest that the simplest answers are not for the individual spaces, but for the alternating sum of their dimensions.
So the X is in the category of smooth representation.
Yes. Homological algebra method suggests that the simplest answers are for the Euler-Poincare pairing, EP pi1, pi2, which is the -1 to the power I dimension of xi. These hopefully more manageable objects, certainly more flexible when coupled with vanishing of higher x when available, may give theorems about Hom spaces. Okay, we hasten to add that before we can define Euler-Poincare, one needs to prove the finite dimensionality of the xi spaces when pi1 and pi2 are finite length admissible representations, and also prove that they are 0 for I large. Vanishing of xi for large I is a well-known generality. For reductive p-adic groups G considered here, it is known that xi are 0 for any two smooth representations whenever I is greater than the split rank of the group.
Sorry, in this question, pi1 is on the big group and pi2 is on the small group.
This is the notation which I use always. Pi1 is on the big group, pi2 is on the small group.
But when you're considering x, is it interesting also to go the other way?
Yeah, the questions of this kind will come up in the course of this lecture. Yes, indeed. Yeah. But this generality that I talked about xi being 0 for I greater than split rank is for any two representations of the group G, any two smooth representations. This is a standard application of the projective resolution of the trivial representation of G provided by the Brouhard-Titz building associated to G. So Brouhard-Titz building gives rise to a certain projective resolution of length equal to the split rank of the group, and therefore xi is beyond the rank vanished. For the proof of the finite dimensionality of xi, we note that unlike the Hom space, where we will have no idea how to prove finite dimensionality if both pi1 and pi2 are cuspidal, because cuspidal representations are a bit mysterious. One would not know how to calculate the dimension of the Hom space. Exactly, this is the case we can handle a priori for I greater than 0. Almost by the very definition of a cuspidal representation, they are both projective and injective objects in the category of smooth representations. So xi's are vanishing for cuspidal representation. Finite dimensionality of xi when one of the representation is a full principal series is achieved by an inductive argument both on n. So here I'm talking about SON plus 1 to SON, and on the split rank of the levy from which the principal series arises.
So can you clarify what you mean by the second part of the first sentence, where we have no idea how to prove finite dimensionality? I thought this was something you were saying we knew.
The finite dimensionality?
Yeah.
Finite dimensionality is achieved by some inductive argument, because one is looking at pi1 on SON plus 1, pi2 on SON. And if one of the representation is a full principal series, then one can do some kind of a Mackey argument to get some way to understand the restriction of the representation pi1 from SON plus 1 to SON. There is some
inductive. I was asking about the first paragraph.
First paragraph. Yeah. First paragraph, I'm saying that you see the Hom spaces for cuspidal representation, I think one doesn't know where to begin, because cuspidal representations are not concretely given. But once you know for cuspidal, for principal series, there is some way, typically what is called the Mackey theory, which allows you to go from cuspidal to the rest.
So I thought you said that we knew for all irreducibles now that this is bounded by 1.
Yes, one knew for all irreducible, but I'm saying that in that argument, somehow the crux of the matter is that one doesn't understand how to prove it for cuspidal. And I'm saying that if instead of Hom space, if we were looking at X spaces, for cuspidal, there is no problem. So somehow, yeah. So in the second paragraph, I say that there is an inductive argument both on the size of the group and on the split rank of the levy from which the representation arises. So the resulting analysis needs a notion of Bessel models, which is also a restriction problem involving a subgroup which has both reductive and unipotent parts. However, there is recently a very general finiteness theorem for X spaces due to Eisenberg and Etan Sayag. So basically, they prove that in situations of Sakellarides Venkatesh for spherical varieties, where the Hom spaces are finite dimensional, typically in those situations, X spaces are also finite dimensional. So there is some generality. However, the approach via Bessel models, which intervenes when one analyzes principal series representations of SON plus 1 when restricted to SON, has as a bonus explicit answers about Euler-Poincare, at least in some cases. Based on various examples, a clear picture seems to be emerging about the X spaces. For example, we expect that when pi1 and pi2 are tempered representations, X spaces are non-zero only for I equals 0, which is the Hom space. So that is the classical situation. On the other hand, we expect that X space from pi2 to pi1 is typically 0 for I equals 0, i.e. Hom space is 0. So no wonder branching is usually not considered as a sub-representation and shows up only for I equal to the split rank of the center of the levy from which pi2 arises through parabolic induction of a supercuspital representation. So this picture is roughly correct, but not completely, as we will see in some examples. So typically going from a larger group to smaller group, Hom space may be non-zero, but certainly X spaces are typically 0. But going from pi2 to pi1, Hom spaces are 0 and smaller X are 0, and it picks up the largest possible X, which can be non-zero. In the Archimedean case, several papers of Kobayashi study the restriction problem for GK modules in the sense of submodules. So there is one particular paper I mentioned, but I think he has understood the several cases in which submodules exist, which is typically not the case in p-adic groups. There are no submodules. But the analogous restriction problem for submodules seems to be absent in the p-adic case. Okay, so just a few generalities. Given a connected reductive F group G, G will be the locally compact, totally disconnected group of F rational points of the group G, and RG will be the abelian category of smooth representations of G over C. The abelian category has enough projectives and injectives. For instance, for any compact open subgroup K of G, the compactly induced representation is a projective object, and the full induced is an injective object in this category. And therefore, since this category has enough projectives and injective, it is meaningful to talk about extra as the derived functors. Okay, so we already talked about the Euler-Poincare pi prime. Okay, so before I talk about restriction problem from G1 to G2, here is a classical result when one talks about Euler-Poincare of finite length representations on the same group G. So actually on the same group G, also these are not so well studied questions about what is the X spaces. So calculation and understanding of X spaces of the same group, finite length or irreducible representation is not such a well studied subject. But here are some generalities. Euler-Poincare is a symmetric jet bilinear form on the Grothendieck group of finite length representations. It is locally constant in a family of representations. It is identically 0 if one of them is fully induced. And then there is this property of Euler-Poincare as integral over elliptic elements of their characters. So this property 4 is called Kazan orthogonality. It is similar to, if you wanted to calculate Hom spaces, then you will integrate the character of one against the other. So it is an analog of that, but here you integrate it only on the elliptic elements. And it doesn't give rise to Hom space, but it gives rise to the Euler-Poincare. So I think this was conjectured by Kazan, maybe proved by him in some cases, but from what I understand, maybe this is not proven in characteristic P. It was proven by Schneider and Stuhler in characteristic 0, and also I think it is part of Bezhrukov-Nikov's thesis. But also in characteristic 0. Okay. So this is for the same group, finite length representations or irreducible representations. Okay, so several assertions about Hom spaces can be converted into assertions about X spaces. There is some generality about functors and adjoint functors, which we will apply using the Frobenius reciprocity. And it says that it typically says that if Hom spaces have some good properties like the Frobenius reciprocity, then X spaces also carry Frobenius reciprocity. Okay, so the following is a direct consequence of Frobenius reciprocity combined with the previous proposition on adjoint functors, that the usual Frobenius reciprocity works for X spaces. And in particular, it also works for parabolic induction. And the second one is what is called the second adjointness theorem. Okay, so here I begin talking about this specific group GLN plus 1 to GLN. Often these phenomena about classical groups are present for GLN in some simpler form. Sometimes it is too simple to model that what we may want for classical groups, but I think it's indicative in many ways. So we begin by recalling the following basic result in this context, proved as a consequence of the Rankin-Selberg theory. And the theorem says that for an irreducible generic representation pi1 of GLN plus 1 and pi2 of GLN, the Hom space is always one-dimensional. So somehow this is perhaps the difference between GLN and classical groups, that here it is identically one-dimensional, and for classical groups it is not one-dimensional, it is less than equal to one-dimensional, and you have to add a lot of things in the L packet, and then you have to worry about which one appears and the epsilon factors, etc. But in some sense, I think this theorem is somehow at the basis of developments for classical groups. So the following theorem can be considered as the Euler-Poincare version of the above theorem, and is much more flexible than the previous theorem. And the point is that it's also proved more easily. And it is a theorem about Euler-Poincare. And unlike the previous theorem, which is only for irreducible and generic representations, this theorem about Euler-Poincare is for finite length representation. So let pi1 be an admissible representation of GLN plus 1 of finite length, pi2 of GLN of finite length. Then the X spaces are finite dimensional, which I already said. And the point of this theorem is that the Euler-Poincare is something very simple-minded. It is product of dimension of the Whittaker space for pi1 with the dimension of the Whittaker space for pi2. And yeah, so WH pi1 denotes the space of Whittaker models for pi1 and WH pi2. So yeah. The proof of this theorem is accomplished using some results of Bernstein and Jelvinsky regarding the structure of the representations of GLN plus 1 restricted to the what is called the metabolic subgroup. Recall that En, the metabolic subgroup of GLN plus 1, consists of matrices whose last row is equal to 0, 0, 0, 1. For representations of GLN plus 1, Bernstein-Jelvinsky define their derivatives, pi upper I, the ith derivative of pi, which is a representation of GLN plus 1 minus I. Of crucial importance is the fact that if pi is of finite length for GLN plus 1, then these derivatives are representations of finite length of GLN plus 1 minus I. Bernstein-Jelvinsky proved that the restriction of an admissible representation of GLN plus 1 to the metabolic has a finite filtration whose successive quotients are described by the derivatives. And this metabolic En contains GLN, and therefore Bernstein-Jelvinsky theory allows you to understand representations of GLN plus 1 restricted to GLN in a rather explicit way. And this metabolic is somehow there only for GLN plus 1 and not really there for classical groups. And I think that is one reason why the theory for GLN, many theories, local, global, and all, are easier to describe. Using the Bernstein-Jelvinsky filtration and a form of Frobenius reciprocity for X groups, the theorem eventually follows from the following easy lemma. And the lemma says that if V and W are two finite length representations of the same group, GLDF, then if D is greater than 0, then the Euler-Poincaré is 0. Whereas if D is 0, which means that we are looking at GL0, which is the trivial group, then of course Euler-Poincaré is dimension of V times dimension of W. So the statement about the Euler-Poincaré eventually comes from this case D equals 0.
So sorry, this is coming from the fact it has a center, is that right?
It comes from a central extension, central characters. Because in a smooth family, the Euler-Poincaré doesn't change, and you can perturb the family by twisting by determinants. Yeah. Okay, so some remarks on the non-vanishing of X groups. One knows that they are irreducible generic representations of GL3, which have trivial representation of GL2F as a quotient. Similarly, they are irreducible non-generic representations with generic irreducible representations of GL2F as a quotient. For each such pair, it follows from our theorem that the Euler-Poincaré characteristic of pi1, pi2 is 0, because one of them is non-generic. But the way we have set it up, in that case, Hom spaces are non-zero, and therefore it means that some X are non-zero. So, right, I mean, one may somehow create a theory about X spaces, but one doesn't know whether they are 0 or non-zero. And it shows that at least in some cases, there are some non-trivial X. The following conjecture made by the speaker several years ago seems to be at the root of why the simple and general result of the previous section on Euler-Poincaré translates into simple result about Hom spaces for generic representation. So I proposed this conjecture many years ago that for generic representations, the X spaces are 0 for all I positive. Okay, so this conjecture has recently been proved by K.Y. Chan and Gordon Savin. It appeared only very recently. So I should add that something slightly stronger than this may be that not only are the X spaces 0, but I think the better property would be that pi1 restricted to GLN becomes a projective module. So that would be better than proving that X are 0. However, one cannot remove the genericity condition for either pi1 or pi2 for the vanishing of X groups. In particular, one cannot expect that a generic representation of GLN plus 1 restricted to GLNF is a projective representation of GLN. Although this is easily seen to be the case for supercuspidal representation, and it is proved by Chan also for discrete series. The following paper of Chan gives a complete classification of the irreducible representations of GLN plus 1, which when restricted to GLN are projective modules. It proves that any discrete series representation of GLN plus 1, in particular the Steinberg, is a projective module when restricted to GLN. So yeah, that's also a recent paper. As the Steinberg representation of GLN plus 1 restricted to GLN, if it is a projective representation of GLN, one knows that all the higher xi's are 0. It follows from a duality theorem of Schneider-Stuhler below that Steinberg contains no irreducible submodules. So Steinberg has a lot of cosents. Any generic representation is a cosent, but it has no submodules. So in fact, Chan has proved that the Hom space, Hom from the smaller group to the bigger group is always 0 unless both the representations are one-dimensional. So there is a complete answer. Okay, so I think this section is a bit work in progress. In some sense, one is trying to understand some properties of restriction from GLN plus 1 to GLN. And there is this theory due to Bernstein about what is called Bernstein blocks. And somehow one would like to understand the decomposition from GLN plus 1 to GLN in terms of the Bernstein blocks. So recall that according to Bernstein, the category of smooth representations of a p-adic group can be decomposed into Bernstein blocks indexed by pairs M, rho, where M is a Levy subgroup of the group and rho is a cuspidal representation of the Levy subgroup. The pair M, rho taken up to G conjugacy and inertial equivalence up to twisting by unramified characters. Now one can ask to decompose a representation of GLN plus 1 when restricted to GLN in terms of the Bernstein decomposition of GLN. And one hopes that there is a nice answer, which in the simplest case is the following proposition. So the proposition is that you begin with any irreducible generic representation of GLN plus 1 and you take a cuspidal datum, but you restrict yourself for those cuspidal datum which under the action of the while group, they don't go to themselves. So the while group has no stabilizer up to unramified twist. And let rho naught be an irreducible representation of rho restricted to M naught. It is the subgroup of N generated by compact elements of the Levy subgroup. Then the M rho Bernstein component of pi 1 restricted to GLNF is what is called the universal principal series. So there is the principal series from P to G of rho, and there is the universal principal series in which you do all the unramified twists also. So the restriction of pi 1 to GLN, and when you look at its Bernstein component corresponding to this block M, rho is very simple-minded. And in particular, the Bernstein component of pi 1 is independent of pi 1. And it has a very simple geometric structure. Yeah, so the above simple-minded description of the restriction problem is not valid for other blocks, such as the most interesting one, the Iwahori block. Which I have still not understood. Okay, so I want to talk a little bit about classical groups now. These sections will be shorter. In the next few sections, we will discuss the Euler-Poincare characteristic for branching laws for classical groups, restricting ourselves to one case, SON plus 1 to SON. We will use Bessel subgroups and Bessel models without defining them, except to recall that these are defined whenever we have quadratic spaces W contained in V with V mod W an odd dimensional split quadratic space. The Bessel subgroup is a subgroup of SOV of the form SOW times U, where U is a unipotent subgroup of SOV, which comes equipped with a character normalized by SOW. So it's a character of the Bessel subgroup. The Bessel subgroup, in the case when the quotient has one dimension, is just the SOW. So Bessel subgroups interpolates from the branching law from SOV to SOW in codimension one case to the case of Whittaker model. So I think it's a various ways of changing the maximal unipotent subgroup of a quasi-split group by making smaller unipotent groups at the expense of putting some reductive groups. So I think Bessel subgroups have been there in works of Patitsky Shapiro, I believe. Okay, so the following proposition calculates the Euler-Poincare in some cases for classical groups. So let pi be a finite length representation of SOV, pi prime of SOV prime, codimension one subspace, and you start with a principal series representation of SOV, where sigma naught is an admissible representation of SOW, and I believe pi naught is a supercuspidal representation of GLM. And in that case, there is a nice formula for the Euler-Poincare, similar to what we saw for GLN. But maybe I don't want to say too much about it. So at least in some cases, Euler-Poincare can be calculated nicely. Okay. So what I want to do next is to review an integral formula of Walsh-Forget, which is an analog of this Kasdan orthogonality in what is called the relative case. I will have occasion to look at it from somewhat different perspective soon. So in this section, we review an integral formula of Walsh-Forget, which we then propose to be the integral formula for the Euler-Poincare pairing, where sigma is finite length for SOV and sigma prime for SOW, where V and W are quadratic spaces. And you know, I have written it in some generality in which W need not be a codimension one subspace, but it is odd codimensional such that the quotient space is a split quadratic space of dimension 2k plus 1. Okay, so Bessel subgroups are defined in this context when you have two quadratic spaces V and W, and the quotient is W is a non-degenerate quadratic subspace such that V upon W, which is a quadratic space, is a split quadratic space of odd dimensions. So this is the context in which the Bessel subgroups are defined. So the integral formula of Walsh-Forget considers the set of elliptic tori in SOW such that there exists a quadratic subspaces WT and W prime T of W such that W is direct sum of these quadratic spaces W, and then V is direct sum like that. And the dimension of WT is even, and SOW prime and this SOW prime plus D plus Z are quasi-split. And T is a maximal elliptic torus in this smaller quadratic space SOWT. This script T denotes the set of orbits for the action of SOW on the set of elliptic tori of this form. For our purposes, we note the most important elliptic torus, which will be the trivial torus, corresponding to WT equals 0. Okay, so for an admissible representation sigma of SOV of finite length, we define a function C sigma T for regular elements of a torus T belonging to T by the Germ expansion of the character of the representation and picking out the leading term. So if this was a regular element not only of the torus but of the group SOV, then it is just the character of the representation. On the other hand, if this T is trivial, then this is related to what is called the Shalaika germ at identity. And for general semi-simple elements, there is what is called Harishchandra descent, which allows you to have functions of this kind by looking at centralizer of that element and looking at the germ expansion. Okay. So similarly for sigma prime and admissible representation of SOW, one has this function C sigma prime for regular elements of the torus T, defined by the germ expansion of the character. And then there is this function delta T on the elliptic torus, determinant 1 minus T. And then there is the discriminant function D upper H, the discriminant function of HR. For a torus T in H, one defines the while group by the usual normalizer by the centralizer. And then here is the Walsh-Forget theorem, which could be considered as the analog of Kasdan orthogonality for the group case encountered earlier. So, what it says is that you define some integrals using these functions C sigma T, C sigma prime T, the while discriminant and the delta function that we define, and you make this integral on the finite sum of absolutely convergent integrals. So you define this number, which is a finite sum, but the integrals need to be proved to be convergent. So his Walsh-Forget's theorem is that if either sigma is supercuspidal and sigma prime is arbitrary, or both sigma and sigma prime are tempered, then this integral gives rise to the dimension of the homospaces.
The calligraphic T is elliptic tori. This is
calligraphic T is a certain collection of elliptic tori, which are not all elliptic tori, but they are decomposed in terms of WT plus W prime T, and these are maximal elliptic tori in SOWT. So not all elliptic tori, but you need to take the decomposition. So this theorem has two parts, that for any irreducible admissible representation, these integrals are finite convergent, and then this sum represents the dimension of the home spaces when both of them are tempered. So in all cases, the integral is well defined, but in certain cases, that integral represents the dimension of the home space. So given the theorem of Walsh-Forget, it is most natural to propose the following conjecture on Euler-Poincaré pairing following the earlier notation. So the conjecture is that the Euler, so here sigma and sigma prime now are general representations of finite length, unlike Walsh-Forget's theorem, in which they were irreducible representations. So one suggests that the Euler-Poincaré pairing between sigma and sigma prime is given by this integral, and naturally, therefore, one has this more general vanishing of higher x. So yeah, so I think this one still seems not considered. Okay, Walsh-Forget's theorem is equivalent to the conjectural statement on Euler-Poincaré if sigma or sigma prime is supercuspidal, except that it is not proved if sigma prime is supercuspidal, but sigma is arbitrary. The Walsh-Forget integral formula is available also in the work of Raphael Buja-Placid for unitary groups. So I think, in the various development on the subject, this integral formula is one of the key formulae. A general integral formula for spherical varieties has been formulated by Chen Wang in a paper which is to appear soon. You know, given that the tori are rather complicated, I think to formulate it in some generalities seems quite impressive. Okay. So just one example of this conjectured Euler-Poincare formula. If either the bigger group is split and sigma is induced from a character of the Borel subgroup of G, or H is split and sigma prime is induced from a character of the Borel, then the conjectured formula on Euler-Poincare becomes Euler-Poincare equals 1. Because in this case, you know, we are looking at character values at elliptic tori, and since one of the representation is induced from the Borel, the character is supported only on, so to say, split torus. So the only elliptic elements on which the character is non-trivial is identity, and therefore Euler-Poincare. So this is the statement on Euler-Poincare which needs to be proved. And this statement is a consequence of one of the earlier propositions. Okay. So in fact, one of the reasons why I speak at some length on Walsh-Perget integral formula, as I feel that it is some kind of a Riemann Rock theorem. Recall that for X a smooth projective variety with Todd class Tx, and for any coherent sheet F on X with Chern class Cf, one has this Riemann Rock theorem, which calculates the Euler-Poincare of X with coefficients in the sheaf F in terms of this integral Todd class against the Chern character on X. And in our case, the Euler-Poincare is conjecturally expressed as integral of the Todd class and Chern class, where X is a certain set of elliptic tori in H. Tx is a function on this elliptic tori, which is given in terms of this y denominator and delta function. So it's something which is associated to X, not to the representations. And then there is this function like Chern character. These are the obtained from the germ values. So C pi1 pi2 is a function on the elliptic tori defined in terms of the germ expansion. So it has
the set X.
X is the set of certain elliptic tori in H. H is the smaller group.
What's the set?
You know, as I said that X is certain elliptic, you know, H is a SOW, and one is talking about decomposing W as W1 plus W2, and H consists of elliptic tori in W1. Conjugacy classes of elliptic tori in W1. W1 is even, so, you know, in maybe we can go back to Walsh-Perget's theorem, in which so here let T denote the set of elliptic tori in SOW such that there exists a quadratic subspace W, W prime of W, such that W is direct sum of these, and of course V is automatic, such that dimension of W is even, and these ones are quasi split, so that one takes the germ expansion and the leading term. And this T is a maximal elliptic torus in SOW. Yeah, so somehow it is a bit subtle formulation, but as I said, Chen Wang has something more general, but I have not read that before. Okay. So next I want to briefly mention a certain duality theorem due to Schneider and Stuhler, which turns questions about Hom space pi1, pi2 to questions about pi2, pi1. And more generally, questions about X spaces, pi1, pi2 to pi2, pi1. And it is of considerable importance to our theme. So the theorem of Schneider-Stuhler says that it is for G a reductive p-adic group, pi an irreducible admissible representation of the group G, d pi is the split rank of the center of the Levy subgroup M of G, which carries the cuspidal support of pi, and d pi is what is called Aubert-Jelvinsky involution of pi. And the theorem of Schneider-Stuhler says that in this particular case, x of d pi d pi is C, and this bilinear pairing xi pi prime cross xj pi prime d pi to xi plus j, so to say the cup product pairing, just like Poincare duality, is a perfect pairing. So this is the paper of Stuhler, Schneider-Stuhler, and we made a small addition to that. So here is an application of the duality theorem to the existence of submodules. The following proposition gives a complete classification of irreducible submodules of the tensor product of two representations pi1, pi2 of GL2F with the product of their central. So this is the triple product situation which I often come back to. So the triple product for GL2 is usually considered as a cosine module, but you can also ask what are the submodules inside pi1 tensor pi2. And here is the proposition. So let pi1, pi2 be two irreducible, admissible, infinite dimensional representations of GL2F with the product of their central characters trivial. Then the following is a complete list of irreducible submodules of the tensor product. So the irreducible submodules are supercuspidal representations of PGL2, which appear as a cosine, so which are understood fully. And then there is one particular case, one more case which happens. So pi is a twist of the Steinberg representation, which we assume by absorbing the twist in pi1 of pi2 to be the Steinberg representation. Then Steinberg is a submodule of pi1 tensor pi2 if and only if pi1, pi2 are both irreducible principals. So somehow supercuspidals, if they appear as a cosine, they also appear as sub because they are projective modules. But except for supercuspidals, there is just one more case of the Steinberg, but that happens in a very particular situation. I think Yannis Sakhaladis told me that he knew about this example, so perhaps it appears in some form or the other in the book of Akshay Venkatesh and Sakhaladis, but I'm not sure. Okay, so here we enumerate some of the basic theorems in algebraic geometry, which seems to have close related analogs in our context, although for no obvious reason. I mean, it's just a template from algebraic geometry. For the analogy, we consider H0 XF for X a smooth projective variety, which has a coherent sheaf F, and this H0 XF for algebraic geometry, and here we have Hom spaces in the context of branching laws. And then the HIH and then the XIH. Okay, so the first theorem which one proves about cohomology of projective varieties is that these cohomologies are finite dimensional and they vanish beyond the dimension. So we have seen such theorems. Then there are semi-continuity theorems. I spoke about some of them. Then there is the Riemann Rock theorem, which expresses the Euler-Poincare in terms of simple invariants associated to the variety X and the sheaf F. Then there is the Kodera vanishing, which says that HI XF are 0 for I greater than 0 for an ample sheaf F. Curiously, here also, you know, instead of an ample sheaf, which looks large in some ways, here we talk about generic representations. And then there is the Sayre duality, which seems to have a very close analog. And of course, in algebraic geometry, it is often emphasized the special role played by the projective space PDF And here we have our own all embracing majesty GLN F, as Hermann Weyl said. So there seems to be a good analogy. Okay, so I want to end my lecture with some thoughts about how to geometrize the X groups. Yeah, so a natural way to construct exact sequence in representation theory is using a proper map X to Z between L spaces carrying the action of the group G and carrying some sheaves. And this gives rise to a G equivariant maps of sections of Z with coefficients in the sheaf G, and you pull back, so to say, I think about this as functions on Z to functions on X. And if the mapping is proper, then it will take compactly supported functions to compactly supported functions. So an example which is more familiar to me is what is called Bernstein-Jelvinsky exact sequence, which arises from the inclusion of an open set X minus Y in a topological space X equipped with a sheaf F, where Y is a closed subspace of X, giving rise to this sequence, which is often called Bernstein-Jelvinsky exact sequence, something which is very commonplace. Nobody will think much about it, but it is one of the central players. Functions on X to functions on Y, there is a restriction map, and if it goes to 0, then it is a function on X minus Y. So this exact sequence gives rise to an element in the Hom space, Hom from Sx to Yf. And this also gives rise to an element in the Xt space, because this is a 3-term exact sequence. So it also gives rise to an element in the Xt space. Note also, and something which seems rather interesting, that the Hom space is from the larger space to a smaller space. Pi1 to pi2, bigger to smaller, whereas X is between a smaller space to a larger space. Okay, so this Bernstein-Jelvinsky exact sequence can be iterated. So if X2, X1 are closed subsets of an L space X with X2 contained in X1 contained in X, endowed with some sheaves, then we have these short exact sequences, 2 of them, and they can be spliced together to give rise to a little longer exact sequence and an element of X2. So as the representation pi2 becomes smaller and smaller compared to pi1, it may be expected to contribute to higher and higher X groups. So various examples suggest that homomorphisms between representations or extensions between them correspond to some geometric spaces or L and L sheaves on them as above. In particular, a typical Hom is from a larger space to a smaller one, whereas a typical Xt is the other way around. Although most geometric spaces have algebraic geometric origins, this is not necessarily the case when thinking about the Bernstein-Jelvinsky exact sequence or this mapping I talked about before that, X to Z, which is proper, because that is topological and that gives rise to extensions of that allows you to construct some X. So I found a particular example using the Brouhard-Titz building very interesting, and I want to briefly talk about it. So for instance, one can use the action of G on its Brouhard-Titz building and its various compactifications. If X is the tree associated to PGL2F, something very popular, then one knows that there is a compactification of the tree in which PGL2F continues to act on the compactification, and X bar minus X is P1F, a closed subset of X bar. The zero skeleton of X, which is the Brouhard-Titz building tree, together with x bar minus x is a compact topological space, call it x naught bar. So, you know, you have seen the tree and there is some boundary at infinity. And here we are only talking about the zero skeleton. So the tree has no branches. It has only those ends and they converge to infinity at P1F. So the zero skeleton has two orbits. One is x naught, which are points inside, and one are points at infinity. There are two orbits. An unramified character of the Borel gives rise to a sheaf on the boundary P1F, which can be extended to a PGL2F equivariant sheaf on x naught bar by making it this particular unramified induction from K to PGL2F on x naught. Call the extended sheaf x naught bar as C chi, and note that the restriction of C chi to x naught is the constant sheaf C, because x naught is the points inside, so they are just discrete set of points. Only at infinity they converge. So the topology is seen only at infinity, where the set of points inside the ball, they converge to the points at infinity. So we have this exact sequence, Bernstein-Jelvinsky exact sequence of this topological space. So the topological space is the set of points on the tree without the stems, and then the points at infinity. And this is the Bernstein-Jelvinsky exact sequence. So since PGL2F acts transitively, etc., so this allows you to construct a certain element of X. And in fact, from some other context, I needed such an X in representation theory. And then I found that it can be constructed using this compactification of trees. So somehow it looked interesting. So it may be hoped that many extensions which representation theory offers may be matched by geometric action of G on topological spaces with finitely many G orbits coming either from algebraic geometric spaces or Brouhakit's building and their compactification. There is then also the issue of proving that geometric actions do give rise to non-trivial extensions. So, you know, I said that there is exact sequence, but as far as I know, I have no general theorems which says that those exact sequences are non-split. There should be some general theorems, but I do not know. All right, thank you.
So any questions?
Yeah.
What kind of condition is it in a family? Like, what does it look like, the locus where there's some jumping in the X?
You're talking about pi 1 to pi 2?
Yeah.
Yeah. I mean, somehow the families are, they don't vary. You know, I think typically the problem is that you induce from new half, new minus half on PGL2, and then there is trivial and the Steinberg. And somehow the jumping happens not in the principal series, which varies continuously, and the representations are typically irreducible, and nothing much seems to be happening. But at this particular representation, it has components, and somehow the jumping seems to be happening at those points. So these are sub-quotients of principal series. And one knows that, you know, principal series reduce in some special points, hypersurfaces.
I was a bit confused.
Yeah.
What you were general discussion and the role of spherical varieties. So most of the discussion was H and U.
You know, it is
So
X tie.
at the end, was that supposed to be much more general?
You know, I think one way to formulate more general question is that X tie of pi1 comma pi2 can be rewritten as X tie of pi1 tensor pi2 check comma C. And then pi1 tensor pi2 check could be considered to be a representation of a larger group, and you are now doing to the smaller group H. And in this point of view, maybe by some Frobenius reciprocity, I think it is equivalent to looking at xi of pi comma the Schwartz space. It is like no, maybe usually if one is trying to think about representations appearing in a spherical variety, then one wants to understand this object. And instead of this object, so X is G spherical variety. And I believe this is what one understands by branching law associated to a spherical variety. And instead of this, one will be just looking at this. So, as I said, Chen-Wang has a theorem which kind of enlarges the scope of Gauss-Purgé's integral formula, and Eisenberg and Sayag have some general finiteness theorem for the modules. Yeah.
In this last part of the talk where you talked about associating representations, like building them from geometric objects.
Yeah.
Do you have any expectation on what the object will look like if the representation is or is not generic? How that will relate to genericity?
You know, generic representations are supposed to be realized by larger spaces.
Okay.
So typically, smaller representations arise geometrically on smaller spaces, and generic representations.
So do you expect that to sort of be mirrored in these constructions?
I guess that's it. Yeah.
Okay. Okay.
You know, there is what is called Gelfand-Kirilo dimension, and Gelfand-Kirilo dimension is somehow related to the dimension of the smallest geometric space on which pi can be somehow realized.
And those are the types of objects we should be thinking about when.
You know, that was a bit vague. I wanted to convey the idea that in geometry there are some extensions. And one would like to somehow hope that up to certain equivalence they account for most extensions. I think one of the problems is that I don't quite know how to. I think there is the question about whether homogeneous spaces perhaps one understands quite well G mod H, but I'm not sure about whether one understands spaces which have two orbits. And I don't also know if you are given homogeneous spaces G mod H1 and G mod H2, what is the way to glue them together in some non-trivial ways. So, and then there is the question of gluing sheaves on G mod H1 and G mod H2 to a geometric space which is obtained by putting them together. So I think even in this example of zero skeleton of the tree and the compactification at infinity, I mean, because it was so simple, I could anticipate what is going on, but I don't know how to, if a space had two orbits and there were sheaves on the two orbits, when they can be glued together in some meaningful way, I don't fully understand.
Is there more questions? Also from Zoom?
Is there an example for a geometric construction for X2? Like,
Say that again.
is there an example for a geometric construction of an element X2?
X2.
Yeah.
As I said, Bernstein-Jellinsky exact sequence is for a closed subspace. And if there is a closed subspace of a closed subspace, then you have elements of X2. So they are there. I have not used them for any purpose.
Okay, if there are no more questions, let's clap and thanks.